Welcome, everyone, to our third edition of Spacetime Conversations with Scientists. And today we have my old friend and the brilliant particle physicist, Dr. Don Lincoln. Don, thank you so much for joining us.
Thanks for inviting me. I'm looking forward to it.
So today, Don and I are going to talk about the biggest unanswered questions in physics, and presumably answer them all over the course of the next hour. No pressure. But before we get to that, I want to first of all sing the praises a little bit of Dr. Don Lincoln. So Don is a particle physicist at Fermilab, and has been working on some of the big experiments there for quite some time. Don, I'll get you to tell us all about that in a second. But of course, Don also has a really spectacular YouTube channel, which is the essentially the Fermilab channel, or at least a good fraction of it. And I checked out the first episode, Don, of your channel. And was humbled to see that it was 14 years ago. And there's an enormous amount of amazing content since then.
Yeah, I've been doing it for a long time. I mean, it was timed well. Made that video a year before my colleagues and I found the Higgs boson, and it was about the Higgs boson. And a reporter at MSNBC picked it up, and it was one of the first ones out there. So it got a lot of views, and that very much helped the channel launch. So yeah, it was fun.
Yeah, we thought we were relatively early with, let's say the hardcore physics genre of YouTube channel, but we are babies compared to you. We're 10 years old. You were doing it before we even, thought that YouTube hardcore science should be a thing.
Well, I'm older than you, so it's natural that I would have started
Sure.
before you. Yeah,
Well,
no,
anyway,
I think I really, really liked the whole YouTube idea when I first saw it. I mean, I saw the potential, and now there's a lot of channels, and it's dwarfed what I hope to achieve. But I'm very glad. I mean, it was very clear that it had such potential.
well, your channel certainly inspired a lot of what what is happening in YouTube science education, and especially YouTube physics, and certainly us. So if anyone hasn't checked out Don's videos on the Fermilab channel, feel free to just drop out of this webinar and do that right now. You have a good backlog library. Um, but uh, but Don, you are not merely an accomplished YouTuber. Perhaps you are primarily a particle physicist. Can you tell us a little bit about the sort of things you work on?
Sure. So yeah, Fermi. I mean, the YouTubing for the Fermilab channel is a sort of a hobby. I mean, it's a hobby I'm passionate about, but my day job is to actually do research. So, as you said, Matt, I'm a particle physicist at Fermilab. I use the world's most powerful particle accelerator, the Large Hadron Collider in Europe, to try and answer some of the questions that don't have answers yet. So we accelerate two beams of protons, accelerate them to near the speed of light, collide them together at the highest energies that have ever been achieved. The temperatures in these collision is 100,000 times hotter than the center of the sun. The last time temperatures like this were common in the universe was about a tenth of a trillionth of a second after the Big Bang. So what we are actually doing is we are essentially in a very small size, we are recreating what the universe was like in just tiny instants after it began. And that allows us as to watch that tiny primordial fireball cool off. And that gives us a sense of how the universe literally evolved from the very earliest moments. So that's kind of the space-time connection to what I do, because it really does allow us to study, the evolution of the universe. But there's the other side of that where we are studying the nature and the behavior of matter in the quantum realm. What happens when you look at things that are really, really tiny and really close together at really high energy? And so, one of the things I really like about particle physics and cosmology are the deep and intricate connections between the two. And it's really, it's kind of mind blowing, at least to me, that the tiniest things can tell us something about the universe as a whole.
Seriously, yeah. Blows my mind frequently. But I guess you have particular experiments that you're most involved with. Can you let us know?
Yes. So at the Large Hadron Collider, there are four big experiments. Uh, they have names that seem to not make much sense called Atlas, CMS, LHCb, and ELISE. ELISE is work on a thing called CMS, which is short for the compact muon solenoid. So compact, you'd think it's small, but that's a lie. The compact muon solenoid is actually 5 stories tall. It's 50 feet by 50 feet by 70 feet. It weighs 14,000 tons. At the center of that detector is where we do the collision. So basically, you want to think of this CMS detector as effectively a very, very fast digital camera, which can take 40 million pictures per second. Now, we cannot record 40 million pictures per second. We just don't have the computer capacity and the tape drives and the disk to do that. So we then have to step down the number of collisions by teaching the detector to pick out the collisions that are more interesting. And we record about 1,000 per second. And so CMS began operations in 2010 at a lower energy than we are operating now. And it's been operating off and on since then. In 2012, both Atlas and CMS jointly announced the discovery of the Higgs boson. And in the intervening years, we have each experiment has published something like 1,200 papers that describe everything from searches to new phenomena to better exploring known physics in a realm that had never been studied before. So that's kind of what we do. And there's a bunch of us. CMS has something like 3,000 uh, uh, PhD physicists working on it, and about 1,000 students or so, something like that. And the other big experiment, Atlas, has slightly more, so above about 3,500 people. So, when I'll be talking, I say, "Well, we did this." It's a really big group, and it takes a lot of people to do that.
Absolutely, yeah. Gone are the days, mostly gone are the days of the lone scientist pulling off some crazy experiment and changing science as we know it. Now it takes 3,000 scientists to pull off something amazing.
And
It's,
decades.
it's kind of the same in astronomy too with our
Yeah,
giant
yeah.
telescopes. And the engineers and all of the
Mhm.
infrastructure, all of the brilliant people.
It's really important for us to acknowledge the fact that the scientists might be the ones behind the crazy ideas, but it's the engineers and the technicians and all of the support people who actually help us build it. And it would not be possible. Any paper I've written would not be possible without, someone wiring this whole thing up, and we're always grateful for that.
Yeah, and also not just putting things together, but also figuring out how to do that,
Oh,
figuring out how to
sure.
make the magnet that powerful, how to you know
Mhm.
not black out Switzerland or whatever the problems are.
Yeah, yeah. And we moved this big detector, this humongous, uh 12,000, 14,000 ton detector. And then when we move it back, it has to be in the same place to within a few microns. And I don't know how to do that.
They don't trust
That
you with that.
yeah, it's crazy.
They barely trust astronomers to go to telescopes these days. We just have to tell the technicians what we'd like.
Right.
Would you pretty please do it for us? Okay, well, amazing. I feel like we'll come back to much of what you're working on as we go through the biggest questions, because these are what you're trying to solve. Um, but uh, but before we jump into those questions, I did want to note that by pure chance, I happen to be wearing the space-time
Mhm.
Higgs boson particle collision T-shirt, which you can purchase right now to support the show, but maybe a little later. And and Don, you thought this might be the CMS detector?
I'm pretty sure it is the CMS detector. I
Yeah.
mean, that looks very much like we had a couple of our collisions that were particularly pretty, and we gave them to some graphic artists to prettify them even more. And that surely looks like one of our Higgs events.
Yeah, you can just do the momentum
Uh-huh.
sum in your head right now and calculate the mass of the Higgs. I assume.
Oh,
I-
yeah, yeah, that's about
Yeah,
125.
is
You
that
can
right? All
tell
right.
just by looking at it. It's obvious.
Yeah. It's the curvy bits. All right. All right. So that was an easy one. Let's get to the hard ones.
Uh,
Everyone, Don requested that we do this episode on the biggest unsolved questions. And so if we can't answer them, it's really on him. But at least Don, I'll do you the service of allowing you to tell us what you think at least some of the biggest unsolved questions in physics are. Do you have a list in your head?
I have a very, very long list, which none of which, I mean, I can't possibly give all of them. Obviously, one very big unanswered question is has an astronomical origin, and that is dark matter. I mean, the fact is that galaxies do spin too fast, and we don't know why. It could be because we don't understand physics, meaning gravity or inertia, or it seems more likely that there is a form of unseen matter that interacts very rarely. So that's interesting because the astronomy world is looking for it out there. Whereas in my accelerator, we're actually trying to literally create it by converting energy into dark matter. So that's one very big, interesting question. Another interesting question, which I think is fascinating and something that we're trying to understand, is Einstein. If you follow Einstein's equations, and Einstein tends to be right about most things, which is amazing. Um, he says, and we've demonstrated that energy can be converted into matter and back and vice versa. But when we convert energy into matter, we make an equal amount of antimatter. So that's number one. Number two, when the universe was smaller and hotter, it was full of energy, and the universe is then cooled. And so you would expect that energy from the early universe right after the Big Bang would have converted into matter and antimatter in equal amounts. But yet, when we look at the universe as a whole, it's made entirely of matter. And so we now know a little bit, and we know that somehow in the very, very tiny first fractions of a second after the universe began, there was a slight asymmetry between matter and antimatter. And for every 1.6 billion antimatter particles, there are 1.6 billion and one matter particles. And the 1.6 billions got together and annihilated, leaving that tiny, tiny residual, which is us. So that's another interesting question. And this is something that we are looking at because we can make matter and antimatter, and we can see if they are created and if they decay differently. So that's another thing we're looking at. Another question that I personally am super interested in is the the what is the ultimate building blocks of matter? And so your audience knows that in maybe 150 years ago, we started to understand the concept of molecules, which were built of atoms, which were built of atomic nuclei with electrons. The atomic nuclei were built of protons and neutrons have inside themselves particles smaller still called quarks. And in my opinion, the data is leaning towards telling us that there is perhaps something inside quarks. Now, that is Don's crazy idea, and nobody should believe that. In fact, this is a very important time for me to remind you that a good scientist never believes what he thinks. But I think that probably something is inside that, and I can't prove that. And that doesn't mean, I mean, and I've looked, and but so I think that there is something trying to, the data is telling us that there's yet a smaller level of matter that we haven't discovered yet. Oh my gosh,
I'm going to get you
there's.
to go into a lot of detail there in a bit, but
Mhm.
believe me, we want to know. All right, but please continue. Let's get your list.
All right, so there's that. Another really very bizarre question is there when you talk to physicists, we say there are four of the fundamental forces, and one can quibble about that, and the count, depending on exactly how you think about it, could be more or less. But let's say there are four, which we often say. Three of them are what we call quantum forces, and one is gravity, which spans the universe. And yet, gravity seems to be outrageously weaker than the others. The others are kind of the same in strength. They're not the same, but they're kind of the same. But one of them is way, way different. And this is something that we really don't understand. So that's another you know, difficult question. Then there is the history. And the history is that we have learned over the years that things that seem different are actually the same thing. The best example of that is gravity. So if you were an absolutely brilliant scientist, the smartest scientist around in around 1650 or so, you would know what gravity is like here on Earth. You trip, you fall down. If you go over a cliff, this is a bad thing because you fall. And then at the same time, you would look in the sky and you would see the planets march through the heavens and the occasional comet and so forth. And it surely seemed that the idea of celestial gravity and terrestrial gravity were different. But then Newton came along and came up with this theory of unified gravity and proved that these two things were exactly the same. And the story repeats itself. There was a time where a lightning bolt and a magnet seemed to have nothing to do with one another. But in the 1870s, um, combining a bunch of experiments and prior thought, James Clerk Maxwell came up with electromagnetism, saying that there's not really electricity and magnetism, there's just one thing. And this has continued into the present time where we now know that electromagnetism and the weak force are actually different facets of a single underlying force called the electroweak force. So we also think that the future, we might see that this electroweak force might actually be or that force and the strong force, which holds the nucleus of atoms together, might in fact be basically the same thing, just looked at slightly differently. And then finally, all of the quantum forces and gravity might be the same force. So this whole concept of unification, we are not sure that that's true, but history has told us that it's true. And so that's another thing that we've been looking for to try and understand if some of these quantum forces can be unified. So far, we've been unsuccessful, but we've done a lot of tests, and so now we know a lot of things that it isn't. And the list goes
Um,
on. There's a lot more
it
things.
it
I
it
mean,
really does.
yeah.
I think if we get through these, we'll be doing well, unless
Mhm.
there was well, these sound like your top, right? These are the ones that keep you up at night.
Exactly.
Yeah. Uh, and, some of these, like, in my head, are clearly connected, and maybe we can pick that apart a little bit.
Mhm.
Um, but, uh, and, does it match my well, let's see, maybe at the end
Yeah.
I'll
What's your list? You have
well,
you have
I
that
mean,
plus.
these are damn good ones. And, certainly they're, um, related to your, you know, field of, chosen field. I mean, a lot of these can be addressed by banging particles together in some way or another. There's other things that are related, like what is dark energy? We have, you know,
Sure.
really no idea, and then it also has its own, as you said, gravity is too weak given what we think. Dark energy also, given what we think, seems to be too weak, or at least the naive ways we calculated it's too weak. So there's this hierarchy problem for both of them. Um, um, uh, the creepiest one is, what the hell does quantum mechanics mean?
Oh God. I, uh, if someone wants me to answer that one, I give up. I don't know. That's hard.
Yeah, exactly. I think maybe we can't even go there, but, that feels like it is a century-old problem. In fact, like 2 months ago,
Hmm.
it was the anniversary. Uh, what happened before the Big Bang?
Hmm.
Why is there something rather than nothing? But we may have, misadvertised. We'll try to just answer most of the outstanding questions in physics, and this is a good list. So I don't know. Let's start at the top. you said dark matter first for a reason. It does it weigh on you heavily, and do you feel that we may be close to spotting this elusive particle, if it even is a particle? And
Um,
is it gonna point the way forward if we do find it?
well, I think it will help. I mean, dark matter is if dark matter is real, and so let's start out. Let's actually take a step really far back. So, as your audience knows, there are a number of unanswered questions in astronomy. Galaxies spin too quickly. Clusters of galaxies, the galaxies within the clusters, move too quickly to be held together. And if you look at the distortion of very distant galaxies, they seem to be more distorted by gravity than you would expect from the gravity you can see. So here's a series of observations, all of whom could be explained by the existence of an invisible form of matter, or perhaps we just don't understand physics well enough, and so our predictions are just wrong. Maybe there's a, uh, a misunderstanding of inertia or gravity or something like that. Now, if you'd asked me 20 years ago, I leaned more towards not understanding gravity or inertia, probably gravity. That was my thinking. But in the last 20 years, the observations of the Bullet Cluster and the Dragonfly galaxies have led me to lean the other way. So now I would say I think it's more likely that dark matter is real. Now, do I know that? No, I don't know that. And until someone either comes up with a better theory of gravity or inertia or finds dark matter, we have to put it in the unresolved category. Now, in my lifetime, we have improved our ability to find dark matter in the wild, so to speak, a millionfold. And we still have no hard evidence for a dark matter that we can observe. We obviously see all the evidence that allows us to think dark matter might be there, but the idea that there's dark matter passing through us here on Earth, we're unable to see it. And there are, as you know, three ways to look for this that people tend to sort of big ways. One is the idea that dark matter exists in our solar system as it would in the galaxy or in deep space, and it's passing through the Earth, not interacting very much. You think of it as like a wind, like ghosts going through us. And so we have built fantastic detectors to try and see that. And so far, those have all had no positive result. There is what we call the indirect way of looking, where you look out where there should be concentrations of dark matter in the universe. And if dark matter has an antimatter equivalent, those might annihilate and form into a type of thing that we can see, whether it be electrons or photons. And photons are the ones that are the easiest to see because they travel in a straight line, even in outer space. Now, the problem with that is, while that is indeed kind of fascinating, there's a whole lot of ways to make high energy photons in deep space, like pulsars or active galactic nuclei and so forth. And so I'm not confident that that will help. That method will be very productive because there's too much we don't know about that wild, crazy universe out there. And so it's very hard to know if we see extra photons, what they are. And so then the
Unless the
final thing,
spectrum is very specific and matches a very specific theory very well,
right,
and is
right, exactly.
unusual in various ways. The
And
final way.
yeah, so even though I like that idea, I'm just very suspicious that we'll ever be able to. I think that will be a confirming measurement, perhaps once we found it some other way. We'll say, oh, well, if that's the case, we should see this out in deep space. And then that might, in fact, be a wonderful clincher of something that we found elsewhere. And then, of course, there are my colleagues where we smash together high energy particles at very large energy, hoping to convert that energy into matter, dark matter, I should say. And that's kind of neat because since dark matter doesn't interact with ordinary matter very much, then that would mean that dark matter would escape our detector. And so what we would be doing is we would be looking for collisions in which energy escapes. And so that is something we've been doing. And again, that has found exactly zero evidence for the existence of dark matter. So, given all that, that might make you and in fact, I have, people who contact me that say, "Well, the fact that you've looked so hard and you don't find dark matter," they start leaning back to the idea of somehow, modified inertia or modified gravity. But I think it could be that simply dark matter interacts via gravity only or interacts with matter, I should say, with gravity only. And if that's the case, it is just simply too weak, and it is going to be challenging, perhaps impossible in my lifetime to find dark matter. I don't know. But given that if dark matter is real, it is 5 times more prevalent than ordinary matter, then it has to have had consequences of how the evolution of the early universe began. And we don't know how dark matter was formed, so that could point to new forces. It could have, significant consequences of the early moments of the universe. So, yeah, I think it's a big thing, and I think solving that will teach us, something really deep about, well, space-time, as you say.
Yeah, it's a thorn in our side, in a
Hmm.
sense that it it feels weird that we've thrown so many experiments at it and just all of them come up zero. Uh, and yet every new theory confidently predicts that it could also that also predicts the existence of dark matter.
Hmm.
Uh, yeah, but it's also as you say, it's quite possible that dark matter is going to be something very inconvenient, like Planck relics, like the
Hmm.
little Planck mass leftovers of primordial black holes that are what 10 to the 20 times smaller than a proton and are almost undetectable. And yeah, we'd have to have smarter people than we currently have, I guess, to think of ways to do it. It's also true that the universe is not obliged to make itself knowable, to to any given generation of technology.
And another humbling thing is when you take what the data allows. There are things forms of dark matter that aren't real. For instance, we know that dark matter isn't um, black holes or something like that because we've looked and we know it's not that. But then when you ask what dark matter could be, there is a range from something like 1/10 millionth of the mass of an electron, which is the lightest particle for which we've measured a mass, up to something like the mass of a large asteroid. So that's an outrageous range, and, you
Mm,
know, the fact that it could be anywhere in there tells us that
mm.
we're kinda clueless.
Yeah, but we're also in an era of certainly in astronomy of rapid advances in our ability to observe the universe,
Mhm.
um, and that includes doing things like really detailed studies of the structure and dynamics of galaxies, and so you
Mhm.
can learn we can learn an awful lot more about the behavior of dark matter, even if we don't
Yes.
detect the particle. For example, the way it clumps together. It sounds simple,
Absolutely.
but for example, if dark matter is made of very long wavelength axions, then
Mhm.
you have galaxy scale interference fringes that we can in principle see, and so there is room for optimism. We should
Yeah,
assume it's
and
going to go.
I if I might interject, as a guy who's been in this business for a long time, when I was a youngster and I was deciding what I was going to do, was I going to be a cosmologist or a particle physicist? And back in the mid-80s when I had to make that decision, the the ability to answer these questions using cosmic measurements was not so great. And so I decided to go in a direction where I thought I could make measurements where I could get evidence and push forward science. But now it's different. Now we really do, as you say, we're able to study things on the cosmic realm that were unfathomable back when I started. And so if someone is interested in these sort of cosmic questions, I think cosmology it's a golden age of cosmology for exactly what you said. We can study things that we never could before. And we it We may not get the answer from those studies, but we will, start ruling out what isn't dark matter and be pointing people that much closer to finding out what the answer is.
So let's I feel like we should move on. So dark matter, it's a gap in the standard model of particle physics in a sense. If it is a particle, it's
Hmm.
it doesn't seem to fit any of the known particles. Uh, and this, obviously the standard model particle physics is phenomenally successful in predicting the behavior of known matter and forces, except for dark matter. Um,
Hmm.
but there are other gaps, and one of them is this matter antimatter asymmetry. There's in the standard model as it stands, there's no mechanism um, very very slightly weighting, as you say, by what is it, one part in
One,
1.6 billion or something like
yeah.
that.
Well, yeah. Okay. So I see that someone asked the question of where's the 1.6 billion come from? So I use that number because that's my calculation. But the reality is there's enough uncertainty in how one does a calculation that if someone said it was a billion to one or 10 billion to one, I couldn't argue against that. But where do we get that number? We get that number by looking at the cosmic microwave background radiation, and that is a residual temperature of the Big Bang, which has, if you look for, back far enough in time, can be, you can draw a link to the matter antimatter annihilation that occurred when the universe was very young. So by looking at the cosmic microwave background radiation, you have a sense of how many matter antimatter annihilations there were. Then you can go and you can do a census of the baryonic matter, the protons and so forth out there in the universe, and that you basically count protons and neutrons. And from those two, you can get a sense, well, there were this many annihilations and there's this much mass out there. And that's where you get the billion to one ish number. And when I did the calculation myself, I got 1.6 billion, but other people say, they round it, well, it's a billion. And some people say, well, since you got 1.6, it's bigger than that, we'll call it 10 billion. So, understand that there is some uncertainty there, but it's not 100 to 1 and it's not a billion to 1. It's of order a billion to 1.
And are we sure that the radiation, the energy budget that we uh in this calculation are assuming came from that kind of last annihilation event as the universe cooled down. Um, can we be certain that that's where it all came from? That all of those photons came from these annihilations?
Um, Probably not, honestly, since we don't really understand how the universe came into being. I mean, there's this idea that the universe, I mean, a current theory, people think about the Big Bang as an explosion, and that's what I call the firecracker model of the universe. And as your audience knows, that's not what the theory says. It says that the universe, something seems to have been there, which then started expanding rapidly. And what that something was is up for grabs. Um, and certainly, whatever it was didn't follow the laws of physics we're familiar with. But then you had inflation, you have this inflation field, which then expanded until it turned off. And then that heated up the universe. So at that point, you have this hot universe, which then should have made matter and antimatter, although some of it probably didn't create matter and antimatter. So there was still energy left over for them to buzz around. But then those particles re-annihilated. So, as you know, the answer is no, not really. Um,
I
and
guess my
that's part of
astronomy
this.
textbook had something like, all right, you have all this radiation, and
Mhm.
because it due to its energy, it's able to spontaneously create these matter antimatter pairs, so that all photons that existed then would have been, you know, at the party of matter
Exactly.
antimatter creation, and then be produced again when they annihilated. So maybe there's no way out. Has to be all of them, or yeah, it's crazy. So I'm vaguely aware that this universe is not mirror symmetric. So there
Hmm.
are charge parity violations, and it's CPT symmetric, but it's not
Right.
C or P or T or any pair of those symmetric. And uh, why isn't why aren't those asymmetries enough to give us the imbalance between matter and antimatter?
Beats me.
Uh,
That's a fair question. Now, so people understand. Well, when we say the universe is not matter antimatter symmetric, that is correct, but it's more complicated than that because if you look at the strong force does seem to treat matter and antimatter absolutely identically, as does the electromagnetic force, but the weak force doesn't. So, and I used to get this wrong. I used to say, well, that matter and antimatter were different. But what we really know is that matter and antimatter are treated differently by the weak force. And so that's like a little string that we might be able to tug at to be able to get a better handle on what this is. So this is one of the reasons why studying the weak force is so interesting because um, originally in 1956 or 7, as I recall, we understood that the weak force really does treat matter and antimatter very differently. And then, but we fixed that up by saying, well, the weak force treats matter and antimatter differently. But if we take matter and in a universe where we have directions, that's exactly the same as antimatter, where all of the directions are reversed. And so that's the CP thing that you're talking about. But then in 1964, we found that, well, that that those two things, the matter with certain directions and the antimatter with the opposite directions, even those were a little different. And that's the idea of this whole CP is violated. But the problem is, and this is the bottom line, is we do see instances where matter and antimatter do in fact act differently. Absolutely. But there's just not enough of it in anything we've discovered to explain why the universe itself is so heavily skewed towards matter. So it's an excellent question. The question you asked is a beautiful, perfect question. I don't know the answer, but the fact that we do see some asymmetries in the behavior of the weak force sort of tells us we should still keep looking in that direction because that's the only place where we see matter antimatter asymmetry. And so recently, and by recently I mean a couple of weeks ago, we saw evidence of um, matter and antimatter asymmetry in particles that are kind of like big cousins of protons, which is something we hadn't seen before then. So, protons, of course, they're built of quarks and they've got up and down quarks. Um, and we don't see the matter antimatter asymmetry in um, how protons are interacting, but with quarks, or sorry, particles that have heavier quarks, they we have found asymmetries. A couple of percent, which is great, but a couple of percent isn't good enough to answer this question. Nonetheless, it's promising, and this is a thing that the Large Hadron Collider was built for. And there was one experiment that I'm not on called LHC-B, and then LHC, of course, is for Large Hadron Collider, and B is for the bottom quark, which it turns out that uh, these asymmetries are easier to see in the heavier quarks, and the bottom quark is one of the heaviest. And so this experiment was built to study just this. And they have, in fact, seen this asymmetry. It's, again, not enough to explain the biggie, but it's a hint. And, I could go into it in a whole lot more detail, but it's very promising and very fascinating. And I don't know what the answer will be.
yeah. Do we need a whole new mechanism? I guess there are specific mechanisms for these CP violations by the weak force, and
Hmm.
I my sense was that the um, LHCb result was uh, you know not so surprising to the people who were looking for it, in that it was a known mechanism. Is that right? And could the same mechanism do what we need with matter antimatter?
Right. So to say it was not surprising, I think is fair. But it only been seen in particles called mesons. So mesons are quark and antimatter quark pairs, whereas this particle is called a baryon, which are three quarks. And that hadn't been seen before. So the fact that we had seen it fairly commonly in the meson sector suggests that we expected to find it in the proton sector, but we didn't know. I mean, physics is an experimental discipline with respect to my theorists out there, but you can have all the ideas you want, but you want to confirm it. So the idea that they were able to confirm this thing, which hadn't been seen. And remember, the first matter-antimatter asymmetry of the kind I'm describing was discovered in 1964, which by my math is 61 years ago. And only now we're able to see it in these baryons and these heavier particles. So yes, I agree with you. It's not like it was a shocking thing to see, but it tells you something about how hard it is to see that it took, almost a person's lifetime to build up the technology to be able to see it.
Absolutely. So you probably answered Hank S's question, which is, has the 1.6 billion to 1 ratio of matter-antimatter asymmetry been observed at CERN? And the answer is not in the context that we explain.
No, 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 no. In fact, the stuff we see doesn't explain. It's just not enough. It's a hint. That's the only way you should think of these matter-antimatter asymmetry we see in particle physics experiments is a hint of a much, much bigger thing that we don't understand.
Okay, so while we're talking about quarks, uh, what's inside a quark, Don? What, what what's the quark lepton substructure? What is the ultimate building block of nature?
My usual joke when people ask me what are quarks is I say it's the noise an Australian duck makes. But um,
Exactly. A quirk,
so
whatever.
so right. So here's the answer. And the answer is I have no idea. Okay. Um, the current standard model says that quarks and leptons have uh, no structure within them. They are particles with, they're what we call point-like particles. So they have zero intrinsic size. And that theory really works extremely well for explaining anything that we've ever measured. However, if you ever look at what we call the standard model picture of particle physics, we find that there are the up and down quarks, which are found inside protons and neutrons. And that's great. That's all you need to build our universe. But then there are carbon copies, what we call generations. So there's a charm and strange quark, which is just like an up and down quark, but heavier, and the top and bottom quark, which is again heavier still. So you have this repeating structure, and we don't know why there's a second and third generation. Now, that in and of itself is a question, but what does it tell us? Well, for some of us, myself included, we like to take an analogy of the understanding of chemistry back in, say, I don't know, 1860 or so, where well, maybe a little after that, where we knew about the periodic table of chemistry. So, for those of you, and your audience knows this, in the periodic table, you have the various columns. Each column acts chemically similar. And as you go from the top row to the bottom row, things get heavier. Now, if you'd asked a brilliant scientist in 1890 what that means, they would say, "I don't know. It's there. It's telling us something, but we don't know what it is." Now, people know that the reason that the individual columns have the chemical behavior they do is because of the configuration of electrons in the outside of the atoms. And we know that they get heavier because as you go down from row to row, you have more protons and neutrons in the center. So that's the real answer. But a broader answer is the mystery of this structure of the periodic table is described or explained by the existence of particles within it. And so it is the behavior governing those internal particles that explains what we see in the chemical periodic table. So we go back to the periodic table of particle physics, and we see this repeating structure where we have a carbon copy of the up and down quark, two of them that are heavier still. Now, I don't know why that's the case. Nobody does. but it just kind of smells to me like a very similar thing, that the thing that will explain this carbon copy is that there are things inside. And what we're seeing is the the hints of the forces governing those smaller particles. So, having said that, nobody should believe any of that. There are theories that have been proposed, gosh, back in the 70s for a particle. We have a name for the particle smaller than quarks and leptons called a preon, and there is no evidence that preons are real, although people have come up with ideas of what they might look like and how they might interact. But when I talk about this, I have to caution people that we've looked. We have looked for the evidence for prions. Heck, I have looked, hoping to find them, and I find exactly zero evidence. Every experiment that we have ever done has is completely consistent with quarks and leptons having nothing inside them. So now I want to take one step back and wrap this question up because I think it's kind of cool. What do we actually know by the measurements? Well, the way that you look to find things inside quarks and leptons is if something is in there, then it's moving around. So there's going to be a size to the quark and lepton. And so what we do is we look for sizes that aren't zero. And to do that, well, if you want to look at something big, you want to look at a marble, you use your eye. If you want to look at a grain of sand, you use a magnifying glass. If you want to look at a bacteria, use a microscope. So you need to use a better, viewing device to look for very small things. So what we did is we used the most powerful microscope on the planet, which is the Large Hadron Collider, and we looked, and we know what's the smallest thing it can see. And that is something of the order about 1/2000th time the size of a proton. A proton is 10 to the minus 15 meters, and we can see the size of protons very easily, but with the LHC, we can see things that are 1/2000th that size. So what we've done is we have looked and we see nothing. So all we can conclude is that if quarks and leptons have something inside them, whatever it is makes an object that is smaller than 1/2000th the size of a proton. That's the real status. So we still see this structure in the fact that we have repeating copies of the different types of quarks and leptons. Don't know what that means, but we know that if there's something in there, it is smaller than 1/2000th the size of a quark and lepton. And there we are. I don't know what it is, but
So,
we looked
Don,
at something.
imagine if you did find that particle, prion or whatever,
Hmm.
how would you know when to stop? The preon's going to have properties. It
Sure,
must give
sure, sure.
the quark its charge and so on. Do you look further down? What does it look like when you get to the bottom of reality? It can't be just the smallest particle, surely. At some point it has to become something different.
Yes, yes. So, I mean, okay, the goal, the real goal of fundamental physics is to devise a theory for which there are no remaining questions. Now, that is an outrageous goal, and that is not something that's going to be discovered in the next decade, 100 years, maybe 1,000 years. But if we ever get to the point where literally our theory does not permit any more questions because all questions are answered, that's when we stop. But any scientist, if they find a question, we're going to dig. And that I think is the answer. Eventually, I hope we will get to that point, not in my lifetime, but eventually.
But there are also major victories on the way to not getting there, and
Hmm.
and one of those could be the which you hinted at in your questions, which is unification. Okay, so
Hmm.
looking for the smallest building block is it's a type of unification in that we're looking for the thing that all things are made of. But there's also this sort of theory unification. We're also looking for the one, set of equations, physical law, from
Hmm.
which all our approximate laws, like general relativity
Correct.
and the standard model, are but special cases. And these
Hmm.
these two must be related. Do you think Do you think that is something that's achievable?
That if it is achievable, I guess I kind of hope so. But your question is a lovely question, but it is something that is incredibly far away from the realm that we can study now. And so I like to do this analogy. So if you ask a theorist, they will say that the energy scale at which unification should occur, where we will finally have the answer, is what they call the Planck energy. So it's a specific energy. Um, but when you ask yourself, what is the Planck energy compared to what we can study now? We can now study things that are things about 10,000 times heavier than a proton, that energy. Um, but it turns out that the jump from the energy that we can study now to the Planck energy is a number of 10 to the 15, which is a quadrillion. So the analogy I give is if the things that we can study now, what the LHC can study is something about the size of the thickness of a cell membrane, the Planck energy is the size of the Earth. So if we took our very best theory of the understanding of the size of a cell membrane, maybe we could stretch it a little bit. We could predict how a cell works. We could learn about mitochondria and nuclei and DNA and all that stuff. But if we tried to project what we understood at the cell membrane scale to the size of the Earth, we would have no clue about volcanoes or hurricanes or the Earth or bunnies or anything. And so I can live with the fact that we are ignorant of that final theory. But what I'm pretty confident of is as we get to higher and higher energies, we're going to discover something that we've never even imagined so far. We're going to encounter some new phenomena and it's completely change our thinking. So I am not so arrogant to think that the ideas that we're exploring now have a really good solid chance of coming up with a final answer simply because we're being guided by something that is so distant from the energy scale at which this might actually occur.
Don, do you think that so LHC found the Higgs?
Hmm.
Many, maybe most particle physicists certainly hoped, but also believed that it would find more.
Hmm.
It's looked to higher energies than the Higgs.
Hmm.
It there was the expectation that there must be some structure in nature there for various well-motivated reasons, including to help the Higgs have the mass that it does, etc. But
Hmm. Hmm.
it seems to be that we're kind of hovering at the level of the Higgs and looking down, and there's nothing as far as we know all the way down to the Planck scale. I mean, uh, there's at least a gap below the scale of the Higgs. Are you surprised at that? Should we be surprised at that?
Surprise. Okay. So, a lot of people, well, sometimes people overpromise. They say, oh, we have some great theoretical idea and we're right around the corner. And if we just look a little harder, we'll get the answer. I was hopeful. I think the right way to describe how I was when the LHC turned on is I was hopeful it was going to change everything. But I didn't like expect it to do. I was just hoping it would. And as it happens, as you said, the universe is absolutely under no obligation to do what we want it to do. So, well, as you said, one of the really tricky unanswered questions, the one that we haven't I didn't even mention, is the mass of the Higgs boson, according to standard theory, should be something near the Planck scale. So it should be really large, but it's not. So there's something taming that. And that new physics, whatever it is, it's going to effectively, I mean, if we just think of this as an equation, there's an integral and there's an upper bound on the top of the integral. And if we go up to the Planck scale, which is the energy at which we know our theories break down, you get a Higgs boson with a Planck-ish kind of energy. But we don't. We get a Higgs boson with a mass of about 125, 130 times heavier than a proton. So that means that there's something is cutting off the top of that integral. And what that something is, broadly speaking, new physics. And so I have hope that that continuing to look a little bit more deeply, we will find something that tames this integral, that cuts that integral off so we don't add up until the Planck scale. But what that is, I don't know. So one person asked in the questions, because there was a theory called supersymmetry that naturally explained all this. And well, supersymmetry it's not something that we found yet. Does that mean supersymmetry is dead? No, probably doesn't. It's very hard to kill a theory completely because you can always say, well, it happens at a higher energy than we can see now. But supersymmetry as an answer to this question about why the Higgs boson mass isn't the Planck scale, it the data disfavors supersymmetry as being the answer for that. Again, we can't disprove it because you can always tweak the theory this way or that so that it maybe still is an answer. But anyways, that was one of the things we were looking for because it was such an elegant answer. If supersymmetry was the way it was portrayed 20 years ago, it would have explained this Higgs thing. It could have been given a an explanation for dark matter. It explained a lot of things, and so people really, really liked it. But it doesn't seem to be the answer. So we just have to dig deeper and think more.
So my understanding of supersymmetry is that the particles don't have low enough mass to cleanly answer the question of the Higgs mass without requiring some, like anthropic argument to choose to get some more of the cancellations there. Is what I'm actually interested from you, Don, is that what is the vibe in the particle physics community? Are people holding on to supersymmetry for dear life? Are they reluctantly letting it go? What's the
No, you know, there are some sort of irresponsible critics of particle physics that painted the world as believing supersymmetry is real. Again, I don't think that I never got that impression within the experimental community. Yes, we hoped. We kind of hoped that that prediction was good. I never believed that supersymmetry was the answer. Now, that doesn't mean I disbelieved it either. I kept a wait and see, which is, I think, the responsible way to deal with science is here is a prediction, and it's a brilliant and lovely prediction. And the right answer for any scientist after that is to say, well, it's bright and it's lovely, but is it right? Let's go test it. And that's what we did. So I would say that the enthusiasm is tamped down a little bit. It's dampened from what it was, where we hoped it would be the real thing. But we haven't disproved supersymmetry. I want to be careful of that. You can't disprove supersymmetry because it could occur at just a little bit higher energy. But what you can do, and what we have done, is said that the way that supersymmetry was was cast 20 years ago, that's not the answer. And I think maybe it's probably worth pointing out because a lot of people think supersymmetry is a theory. Supersymmetry is absolutely not a theory. That isn't. It is more like a principle. So supersymmetry just says that if you take all of the particles that are fermions, so spin, half, three halves, and so forth, and all of the particles that are bosons, so spin 0, 1, 2, and so forth, you have the equations. And if you just swap everywhere in the equation, you put a fermion where a boson was, and vice versa, the equations don't change. That's what supersymmetry is. It just says that these fermions and bosons come into the theory identically and interchangeably. That's not a theory. That's a principle. That's like conservation of energy. Conservation of energy is a principle. It says that if you do things today and tomorrow, the energy will be the same. That's not a theory, right? And so by disproving that supersymmetry was the explanation for this Higgs question, we haven't disproved supersymmetry because that still could happen at some higher energy. The theory could treat fermions and bosons the same. But we have not definitively, but suggestively disproved that this the energy at which this idea that fermions and bosons can be interchanged without noticing is probably, if it exists at all, at a higher energy than we can currently see. So my colleagues, they keep looking because, well, that's what you do in science. You look. Um, but I think most of us are saying, well, if that's not it, the question still needs to be answered. So let's start thinking of alternatives. And so, we have a lot of data. So let's look at other alternatives.
Let's do that. So Don, we're actually at time, but depending on how much time you have, we could do a quick fire of some of the audience questions and see how many
Sure,
we can
let's
get
try.
wrong as quickly as possible.
Do
Um,
you?
so let's see. I'm just going to randomly choose some, and I'm not choosing them for answerability particularly. So Quasar 791, how solid is the idea that spacetime might emerge from entanglement?
Uh, no clue.
Okay.
It's more your world.
Well, it's not my world. I have a meta answer, which is that I got to have a conversation with Juan Maldacena, the creator of ADSC correspondence of EP equals EPR, and he is working hard and thinks that that has plausibility in the context of the holographic universe ADS-CFT, and so the entanglement on the infinite boundary of the universe from whatever quantum particles are there
Mm.
could encode the extra dimension of the interior. That's it. Okay. So
Well, I want to say one thing. Problem with ideas like that is they're fantastic and wonderful, but if you can't test them, then they're just ideas. And I'm not it might be true, but until we test it, I wouldn't
one
take it
also
seriously.
says that a 10,000 qubit quantum computer can create a model universe in a bottle to test this. But all right, we have to move on. This is fast fire, where it's a way away. So Bavander 2, detecting a graviton directly is probably infeasible. Are there indirect ways to experimentally test theories of quantum gravity?
Possibly. And let me just kind of answer that by ducking the question a little bit. There was um, an article in Scientific American. I don't remember the issue, but it was last summer, so the summer of 2024. And what it did was didn't try to find a graviton, but it tried to find interference that would exist in gravity. So it was really a nice experiment that was potentially feasible with close to current technology that showed interference in the force of gravity. So I recommend that people look through the last summer. It might have been somewhere between March and, I don't know, maybe August of last summer. And in Scientific American, there's a really good measurement that I kind of like, and it has the beauty of potentially being testable soon.
Okay, you all have homework. Victor Muller 5702 asks, why is there such a mathematical symmetry between the expressions for the electromagnetic and gravitational forces?
If I think I understand the question, they're asking basically why does the 1 over r squared behavior happen? And that would
Also
actually,
heard
there's
there's
an
like
answer.
a magnetic analog to gravity too, but please go ahead.
Oh, I don't read it that way. I mean, maybe I'm wrong, but I read that as why does Coulomb's law and Newton's law have the same mathematical structure? And that we can answer. And we can answer because that little 2, 1 over r squared, that 2 is the number of dimensions of space minus 1. And so if we lived in a two-dimensional universe, it would be that would be 1 over r, those equations. And if we lived in a four-dimensional universe, it would be 1 over r cubed. The reason that it's a 2 is simply because both electromagnetism and gravity expand into three dimensions. So that's what I think that question's asking. And I think that's absolutely fantastic because that little equation tells us something about the number of dimensions, which is just awesome.
Yeah, super cool. The first time I realized what the inverse square law was saying as a student at some level, I that was part of what the inception of my love for physics, that simple equation encoded so
Yeah.
much about the universe we live in.
Yeah, yeah, and you don't realize it until someone helps you through it. It's amazing. I made a video about that. I forget the one name, probably about number of dimensions. So you want someone should look for that.
All right, last quick fire. Do you think there's deeper physics behind neutrino oscillations that we've yet to discover? Will we find right-handed neutrinos?
I don't know. I mean, that so Fermilab is spending a lot of time and a lot of effort looking at the behavior of neutrinos. So, if we see right-handed I mean, there's nothing that says that right-handed neutrinos don't exist. All we know is that right-handed neutrinos don't interact via the weak force. I mean, that's really what we know. What right-handed neutrinos could exist, and we do look for them. And if they exist, well, there's a lot of possibilities of what that means. Everything from it's a form of dark matter, which is one possibility, to having something to do with matter and antimatter asymmetry. If we, given that we see that all neutrinos that we've ever seen, meaning all that interact with the weak force, are left-handed neutrinos, and all antimatter neutrinos are right-handed neutrinos. If we see a neutrino that's right-handed, maybe it'll tell us that um, matter and antimatter neutrinos are actually the same thing, which is a kind of a cool idea. Which isn't the true same for electrons, which matter and antimatter are quite different. So we're looking, and our big experiment will turn on in ballpark 5 years or something. And one of the things it's really looking at is the oscillation behavior of matter neutrinos versus antimatter neutrinos. And if they're different, that is going to tell us something fascinating.
And could answer at least half of the big outstanding questions that we talked about today, possibly more.
Maybe,
Dark
maybe.
matter, matter-antimatter asymmetry. Yeah, I don't know. It always blew my mind. Why shouldn't they be right-handed? But we wouldn't see them. But why shouldn't they? Anyway,
Yeah.
we're on the edge of our seats for 5 years waiting for that one. So,
Hmm.
guys, we are over time. This was too exciting to end on time. Don, are there any last words? Anything you'd like to tell the crew? Secrets to reveal?
No, no, no secrets. Just you have to watch what we do. I mean, the fact is people like me and Matt, we're explorers. We're pushing back the frontiers, and exploring is hard. We go down blind alleys and so forth, and it's easy to be impatient and expect that we'll know the answer right soon. But we don't. We're sort of stumbling in the dark, hoping to come up with something that changes how we think about the universe. And so I very much appreciate the audience, the people who are out there who are curious. And there's a YouTube video or channel that says it all. Stay curious. I hope you do. It's wonderful. And if you keep watching, my colleagues and I and Matt's colleagues and I will tell you the hints when we figure them out.
And let me add, there's something you said before we started, Don, which is that there is a lot we don't know. There's so much more, well, that we do know, and despite the fact that there are huge unanswered questions. I mean, a couple of things. That doesn't mean that the space of possibility for those questions is wide open. We are honing in so many cases and building this gigantic knowledge structure around these these shrinking gaps in our understanding of the universe. And as you mentioned, Don, it's often when we express our uncertainty in the universe, really we're just being scientists and honest. But it's very easy to take that as, well, you don't know anything yet, and uh, not true. We know one or two things, and certainly one of them is that our universe is spectacular, complex, um, completely self-consistent, and amenable to our scientific inquiry.
Right. The universe is ultimately knowable, even if we don't know it.
All right, everyone. Thank you so much for joining us, Don. Thank you for being here, enlightening us, and we'll see you all on the internet.
Well, thanks for inviting me. I very much enjoyed it.